We started looking at differential equations last unit, although we've really been looking at differential equations all along, because the definition of a differential equation is simply an equation involving a derivative, and we've been doing that all year. So you've been working with differential equations. We haven't really talked about the order of a differential equation so far, but it's a simple thing. The order of a differential equation is simply the highest derivative involved in the equation. So if I have a differential equation and I've written it as, let me change my color, dy dx equals x squared, that would be a differential equation of order 1. If I had, where I had, f double prime of x equals x squared, then that would be a differential equation of order 2, and so on. So it's just the highest order derivative, or the highest derivative involved, which is the order of the differential equation. We will be dealing with mostly first order differential equations, although we will have some that are of a higher order as well as we go through these different problems that we'll be working. Alright, so let's look at some examples. Example 1. We want to find all functions y that satisfy the differential equation dy dx equals secant squared x plus 2x plus 5. So this is asking for a general solution. So it's that family of functions, all the functions that will have this derivative. So if you remember from last unit, we would write out the function dy dx, the differential equation, equals secant squared x plus 2x plus 5. And then we would write it so that the dx moved over to the side with all the x's. And if we had had any y's, we would have them be on the side with the dy. And then we integrate both sides. So we end up with y equals. And so we know that the function that has secant squared x as its derivative is tan x. And we know that the function that has 2x as its derivative is x squared. And the function that has 5 as its derivative is 5x. And then we put the plus c at the end because it could be any vertical translation of this particular function. Y equals tan x plus x squared plus 5x plus c. So all functions y in this form, where c is a constant, will have the given derivative, and they are the solution, general solution to this particular differential equation. Well, as we move on to example 2, we're going to go from talking about general solutions to particular solutions, and this should be a review. We've done these before, but we just want to go over the vocabulary again. A differential equation with an initial condition is called an initial value problem, and it has a unique solution called the particular solution to the differential equation. This just means that instead of the family of functions that we get as our solution, we're going to get just one equation that it will have the given derivative, and its graph will go through a particular given point. So the first step is to find the general solution, and then we will use that initial point to find the particular solution. So we've got dy equals e to the x minus 6x squared dx. And we're going to take the integral of both sides. So we end up with y equals e to the x minus 2x cubed plus c. Alright, and now we will use the given point 1, 0. That just means that when x is 1, y will be 0. So we go ahead and substitute everything in, and we'll solve for C. Ooh, that's a messy 3. Doing this on my iPad, so it's a little hard for me to write very neatly on this. I apologize. Okay, so then that's going to just mean that we got 0 equals e to the 1 minus 2 plus c, and so c will equal 2 minus e. All right, and then the particular solution is going to have that filled in for the c right there. So our particular solution will be y equals e to the x minus 2x cubed plus 2 minus e, because that's c. So that right there is the particular solution. And if we graph that, it will go through the point 1, 0, and we'll have the derivative of e to the x minus 6x squared. So an initial condition determines a particular solution by requiring the solution curve pass through a given point. If the curve is continuous, this pins down the solution on the entire domain. But if the curve is discontinuous, the initial condition will only pin down the continuous piece of the curve that passes through the given point. In this case, the domain of the solution must be specified. So if you have a graph that's discontinuous, then we can only talk about the particular solution for the piece that contains the point in the initial value problem. So let's look at an example, and I'll show you some graphs so that you can see what's happening. Example 3, find the particular solution to the equation dy dx equals 2x minus secant squared x, whose graph passes through the point 0, 3. So we have dy dx equals 2x minus secant squared x dx. And we'll integrate both sides. And so we're going to have y equals x squared minus tan x plus c. And that is the general solution. Now I want to show you a graph that has three different solutions, or the solution with 3 different c's. I'm going to have one that's x squared minus tan x plus 3, x squared minus tan x and c is 0, and then x squared minus tan x minus 3, just so you can see what this graph kind of looks like. Okay, so there it is. All right, so if you look, the graph in red is x squared minus tan x, c is 0 there, and then the blue one is plus 3, so it's been shifted up 3, and the green one has been shifted down 3. There are a bunch of different discontinuities to this particular graph. You have a discontinuity, a segment here, a segment here, and then you've got this segment here where the shifts are affecting it. The other two you can't hardly tell, they're so steep. You've got this segment right here, you've got this segment up here, and then you go back, and there's actually more to this graph as you go out to the right as well. So notice that we have all of those different segments in there. So we are going to be dealing with that segment that's right in the middle, because we're dealing with where x is 0. And so that's the only piece we're going to be able to talk about in our particular solution. All right, so let me get rid of this. Okay, so we are looking at the particular solution 0, 3, so that means that when x is 0, y is 3. And so when that happens, then we have the tan of 0 is 0, and so c equals 3. So our particular solution is y equals x squared minus tan x plus 3, but now we have to limit that domain. So this looks complicated. It's not. We know that x squared is continuous everywhere. We know that tan x is continuous, but then it has those discontinuities at the pi over 2's, 3 pi over 2, negative pi over 2. And since x is 0 in our initial value, then we have to narrow down that segment. So 0 is in the continuous segment for tan x from negative pi over 2 to pi over 2. And I made a mistake. I'm sorry. There should not be equal signs, just less thans, because of the asymptote that's there. So when we write our solution, we have to write it where we have the y equals x squared minus tan x plus 3, but then we have to show that x is limited to the interval from negative pi over 2 to pi over 2. Yes, the graph goes on beyond that, but we can only talk about the segment that contains that given point. So it seems complicated. You'll get some practice with it, but it's really not too bad. Now we're going to look at how to deal with solving a differential equation when we have an equation that we don't know what the integral or the antiderivative of it is. Okay, so example 4, find the solution to the differential equation f prime equals e to the negative x squared, for which f of 7 equals 3. So what we have is, and we can write it, you don't have to, you can leave it as the f double prime, but what we've got is this. And so then we would write dy equals e to the negative x squared dx. And we would take the integral and y equals, and now we have to stop because we don't know what that antiderivative is right there. And so we're kind of stuck. But we can use our fundamental theorem of calculus number 2, the one we call number 2, to help us solve this problem. Because what we know is e to the negative x squared is a derivative. Okay, so this is a derivative. And we know one function that has it as its derivative, and it would be a function that looks like this. Well, maybe not that because it's messy. Let me try again. That looks like this, right? Where we have x in our limit of integration. And so then we're like, well, what number needs to be at the bottom? And that's where our initial condition comes in, because we're going to put that 7 right down there. If we were to take the derivative of this integral, then by our second fundamental theorem, we would get e to the negative x squared, because you just plug it in, multiply by the derivative of x. So we can write that here, and we're going to do it as 7 to the x, e to the negative t squared dt. Okay, now what I need though is I need for this function to equal 3 when x is 7. And so this is our plus c, and I need to know what that c is going to be. Well, if you remember, one of our properties of integrals says that when the limits are the same, then that is going to equal 0. So if I have this function as my solution, when I plug in 7 for x, I'm saying that this is y of x, when I plug in 7, I would get 7 to 7 plus c. But I need that to equal 3, and so C is going to be 3. So then our solution to this particular problem, I'm going to rewrite it as f, since that was the original problem, equals the integral from 7 to x e to the negative t squared dt plus 3. It's gross and disgusting. You won't have to do that very often, but it's a good thing to look at. It brings in our properties, it brings in our second fundamental theorem, shows us how we can use it to solve differential equations. And if we needed to evaluate this, if this actually represented, a real world example, a word problem or something, we could plug this into our calculator and actually evaluate it. So there is some practicality to it. You won't have to do it a whole lot, but hopefully you understand the steps that we went through. And if not, we can talk about it some more in class tomorrow. We're almost done, so hang in there. All right, let's look. So this one just says graph the family of functions that solve the differential equation dy dx equals cosine x. All right, so dy equals cosine x dx, and y will equal, so we take the integral of both sides, sine x plus c. So there's our family of functions. As we've talked about before, these are simply translations, depending on what C is, translations up or down, vertical translations. And so in general, a quick picture of what that's going to look like is something like that. Of course, it would be much denser. These would be, overlapping because there's an infinite number of translations in between each one of these graphs. But this is basically the general idea of what this family of functions is going to look like. That's the sine graph translated up and down. We're going to need this idea as we move into our next section, which is slope fields. So just keep in mind that this is what's happening with our general solution, that the graph is just all of these vertical translations of the solution to the differential equation. All right, have a good evening. I will see you in class tomorrow.